Okay, so this video is the first of several on related rates problems, which are modeling, sort of more modeling problems with derivatives, different than optimization problems. Although some similarities in that there's these will be word problems. So, but in any case. It's yet another application of the derivative, probably the most sort of get your hands on it sort of a application in terms of this is, just sort of modeling at its purest form of saying I've got a system and I want to write down the math that models it, that represents it, and, ask and answer some questions about it. So as usual, I'll just refer you, or remind you, I should say, to, really as we're going through these with word problems, as always, it's really difficult. It's the challenge is getting them set up in most cases. It's not so much the solving. That's fairly, robotic. But it really is the setup. And anyway, you've done lots of word problems throughout your lives, and you already have an appreciation that they present a unique challenge. So as we go through these, and we'll do lots of examples of them together, really, again, try to understand, wait, what is this step? Why are we doing this? It's really not going to be sufficient to just try to memorize problems or types of problems, because I will give you ones that you've never seen before on an exam that use the same strategy, but are not necessarily the same exact setup as one that you've seen. So really try to get that in. As we go through this, I'll certainly be explaining, why we're doing everything, but make yourself some extra notes maybe of, oh, okay, we did that because blah, blah, blah. And that probably will really be helpful for you later on when you go to try problems of your own. So let's get started with these. I will. There's a handout that goes with this, which is posted. I'll flash over to that when we get there. But there's a handout that you probably will want to print out. Actually, let me do that right now. So if you go onto our Canvas page, you should see. Down here in the assignments or lectures portion, this week's stuff. And when you click on it, there's a handout right here. And that kind of is what I've just put on the slides that I'm about to scroll through. Although at some point it's kind of just a pain in the ass to put all the stuff on there. So I'll just refer you back to the sheet. But the point is if you click on that right now and open up that document, it's this is the document that you'll see. It starts there. And this is basically just what's going to be the next few videos, is us going through this document. As you can see, it's 4 pages. The first page is sort of, I guess, the sort of lecture part or the instructional part, I suppose. And we'll do all of this together. And the bottom of the first page is sort of the strategy guide, I guess, or the steps that you might take, which are also I cut and pasted into some slides. And then what follows on the 3 pages after are examples and problems to work through. So I didn't cut and paste those because it was kind of a pain. But we will do these together. So if you want to, it's not a bad idea to go ahead and print this whole document, and that way you can just sort of fill it in. I left space, as you can see, for you to fill in what you do, blah 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 everywhere. So if you want, you can print this. If not, at least have this open. Maybe off to the side as you're watching the video, so that you can refer back to it. And if you want, you could just sort of copy these problems into your notes if you don't want to print out this paper, this handout. So, okay, back to this. All right, so related rates. So what is this all about? So a couple just sort of introductory things just about modeling in general. So one thing I'll say, so what is modeling? Just sort of as a term, really just means, coming up with a way of applying math in this case. It could be any sort of science, but for us it'll be applying math, meaning algebra, calculus techniques, to real world problems. So if I say I'm coming up with a model for whatever physical situation, for a pendulum swinging back and forth. Okay, a model of that is some function in that case that represents, I don't know, the height of the pendulum or the whatever it is you care about. So modeling just means basically word problems. I mean, in all, that's basically all they are. Maybe with the special attention in our problems to sort of more physics-like problems, and by that I mean objects in motion, I guess, and physical movement or physical processes, maybe not necessarily movement, is where all of our examples, I think pretty much all of our examples will come from, is trying to model a physical system that's changing. Okay, so that's really, when we say modeling, that's probably the best way to think about it, is I'm trying to come up with a way of putting math or introducing math into a physical system that is somehow evolving or changing, and I want to be able to capture that evolution and change with a function or functions. And why? Because once you can kind of leave the real world and get on paper, so to speak, the math world, you can do all kinds of stuff without having to, actually physically be in the real world doing things. So in other words, if you're trying to observe and understand some physical process, some physical system, as soon as you have a good model for it, you can stop observing the actual physical process and just go with your model and say, now I can make predictions about what's going to happen a year from now. Whereas how do I do that without science? I literally have to wait a year and be like, oh, see, this happened. Well, that's, I mean, nobody's going to pay you any money to make a prediction a year in advance that you have to wait a year in order to make, right? So modeling is very important, right? And being able to sort of capture a physical system and represent it, to be able to basically study it and maybe make predictions and all kinds of computations about it. So immediately, one significant difference between, I guess, these problems and ones we've mostly dealt with so far is that as we will be trying to, or well, we will be, I'll say, as we will be trying to model a physical system, a real, real something that's really happening. That's changing over time. Okay, modeling a system that doesn't change is pretty dumb, right? I mean, if something is always the same, I don't really have to come up with a very fancy model for this, right? If you cut a piece of wood and it's 4 feet long, I don't need to come up with a function that represents how long will that piece of wood be in a year or in 5 years or in 20 years, because unless you do something to it, it's always going to be 4 feet long, right? So that's not what I'm talking about. But if I was to say, I take that piece of wood and I put it out in nature where there's, rain and wind and all this other stuff that might cause it to decay. Well, okay, now maybe it is interesting to ask the question, how long will that piece of wood be in 1 year, 5 years, 10 years? Because it's probably changing due to erosion and stuff like that. Okay, so in any case, we're going to be, like I said, the main sort of character, I guess, in our story with these problems is that a thing or things in our problem will be changing over time. And by over time, I mean over the course of the problem that we're talking about. And so, to that effect, since we're trying to model something that's changing over time, we will use t, obviously, for time, as our variable. Okay, instead of x, right? So I realize this isn't probably a huge crisis in your life, right, to say, okay, now everywhere where we did stuff with x's, now we're going to do it with t's. So, the entire derivatives chart that you became accustomed to, which has x's all over it, okay, those are all t's now. Great. Who cares? It's not a big deal, right? Okay, so that's one change or one thing that's different about these problems is we'll use t pretty much always, I think, as our variable. The other thing to just note then is to say, okay, so if f of t is some quantity at any time t, right? So just to remind ourselves, do we understand all of the notation and everything, right? Then I'll just say a couple of comments here. One, you know, f of some number then, right, whatever you want, 2 for example, is you know, just so we're all clear, right? When I plug a number into this, like 2, for example, as I just made that up, but f of 2 would then represent, well, how much of that quantity do you have at time 2, right? So if f of t represents the weight of some object at time t, then f of 2 would represent the weight of the object at time 2. Okay, I guess that's pretty obvious, I hope. So, all right, that's easy enough, I think, right? And literally, if I have a formula or some expression that's got for f of t, if I plug 2 in for t, yeah, sure, that tells me how much do I have at time 2. Great, that's easy. But what I wanted to call your attention to then is you know, what do I then think about for the derivative? And this is where, again, thinking about what does the derivative represent, which I know for us slope is a good synonym, and it is. But really for related rates problems, I want to think about, well, what's the derivative represent? Well, the derivative, as always, is, you know, rise over run or the slope. And that's true. Those kind of are more graphical interpretations, though, right? You think of slope, you kind of, hopefully, you think of a graph, maybe. And that's nice. But here, with word problems, a graph isn't so much where we're headed, where we'd like to stay. Instead, I want to think about, well, what is this quantity? And if I say take the derivative of f of t, so f of t is how much do you have, or how much is this at time t? So what's the derivative? Well, that should be the rate at which that quantity is changing at time t. And I have to say, this is a very important thing to remember. So the derivative then, right, is and I'll put this word in caps, right, is the rate at which whatever this quantity is, this quantity changes at time t. Okay, so a very important thing to understand, I guess, is I can't probably emphasize this enough, how important it is to really be thinking, because it's word problems, right? So you're going to be seeing, it's words, right? So you're going to have to sort of think, well, all right, they're saying that something is 7. Okay, yeah, I see the number 7 there. What is that? Is that the amount I have? Is that the rate at which it's changing? Is that the time 7, right? So you have to be very careful and very clear on when you have numbers in a problem, what do those numbers represent? If you have a number, if I say f of 2 is 7, that means you have 7 whatever pounds or 7 feet or whatever it is at time 2. But if I say f prime of t is 7, not the derivative, right, then I'm saying the rate at which this quantity that I'm studying changes at time t is 7. 7 feet per minute, 7 miles per hour, 7 pounds per week, okay, whatever your time units are. So the derivative is always going to represent the rate at which a quantity changes. And this will become clear. I'll probably say this 5,000 more times in these videos. You have to keep it straight in your head. What quantity are they asking us about? And, you know, there's a giveaway, right? There's a dead giveaway, which is that if you see the word rate or some sort of synonym of the word rate, like how fast is something changing, that's asking you about a rate. If you see something like that, those are always going to be referring you to the derivative, not the function. Okay, and we'll see these throughout. But again, just keep that in mind, especially This is something I know students have a lot of trouble with, and that they're, unfortunately, no matter how much I emphasize it, are still going to plug things in for the wrong thing. So just try to sort of keep that in mind as we go throughout these problems, that the derivative, really for us now, if your synonym for derivative was slope before, try to think about, in these problems, your synonym for derivative is rate now, right? And rate, I think is just an English word. Everybody has a notion of what rate means, right? Rate is the easiest rate to think about, is one that we encounter every day, miles per hour, right? That's a rate. Why? Because it describes a quantity, miles, and how that quantity changes per time unit, hours, right? So 60 miles per hour is a rate because it's saying your car changes position or distance by 60 miles per every hour, right? So that is a rate of change, or a rate. And that's, again, synonymous for us with derivative. Okay? All right, so consider that useful information for now or later. Or now and later, I guess. All right, so before we get to these related rates problems, which are kind of interesting. I mean, I have to say, as much as I try not to geek out too much, they're sort of interesting questions to be able to say, oh, wow, like I could actually compute that. Things like, how does a speed gun, that cops use, a radar gun, how does that really work, right? How does that compute your speed along the roadway? And some of the examples we'll do are a little silly, of course, as always, but these do represent at least interesting questions, and be like, oh, well, how the hell would I have been able to do that? Well, the calculus that we've learned is exactly what's going to help us with those things. So, but before we do that, a couple of things, components, I guess, things we're going to need to be able to do later. And I've found that introducing this later in the midst of all this word problem nonsense leaves students rather confused. So I pulled this out and said, let's talk about just this topic for the next 15 minutes and get hopefully a good understanding of this. And then we'll see this come up when we actually try to do these rates problems. Okay, so one thing that we're going to be asked to do in most of these problems is to do what in math is referred to as an implicit derivative. And I should say I'm on the sheet now, I think. Actually, let me just double check that I'm on the sheet. So if you're on the handout, yes, okay. So if you're on the handout that I asked you to print out, I'm now right at the top with implicit derivatives. And I've more or less just cut and pasted this in. So you should be able to just follow along on your sheet here. Okay? So go back to this. All right, so an implicit derivative happens when you're trying to take the derivative of something, of some quantity, some expression, but it's not something, that we're familiar with taking derivatives of, like sine of t. Remember, we're going to switch to t now, right? Okay, well, I know what the derivative of that is. I can just look that up in the chart. It's cosine of t. Okay. And why was I able to be so specific about my answer? Well, because I knew that I was talking about sine of t, which is a function that's very well described. And so I was able to very perfectly and completely describe to you what the derivative of sine of t is and say, oh, it's cosine of t. Okay. Well, sometimes, and in these problems all the time, you're going to be encountered with the issue that you want to take the derivative of something, but part of what, or all or part of what you're looking at, that you're trying to take the derivative of, involves an unknown function. Okay. So by that I just mean that rather than knowing very specifically that I've got the sine function, I might instead just have an arbitrary function like a of t or f of t or whatever you want to call your function. But I still might want to say something intelligent, as smart as I can say, something about what's the derivative of that. Okay. Now again, I was able to say the derivative of sine of t was cosine of t because I have that in my chart. But if I just have an arbitrary or arbitrary random function like a of t or an unknown function, and I want to say, well, what's the derivative of that? Well, I can't give you a specific answer. I can't say that it's e to the t or it's anything like that. But I can say something about it. Now, sometimes this is going to seem a little silly because what we're going to say about it is oftentimes very basic, but a very important step in these related rates problems. So, and it's a little clearer if I look at something a little bit more complicated. So, but let's do the first couple examples first. So, and I'll just leave this guy up here sort of in the corner just to serve as kind of a, I don't know, comparison between things we already know how to do and things we're learning to do right now. So, if I wanted to say, again, what's the derivative of sine, I look that up in the chart and I say, oh, look, it's cosine. But if I just had a generic function, a of t, which is my first example right here, and I say, what could I say about the derivative? Well, this is, again, what's called an implicit derivative, because I don't specifically know the identity of the function, right? I don't know that a of t is really one of my famous guys that's in my chart. I have to just sort of treat it like it's, well, it's some function, any function, or you could say that too. So I'm sort of seeking out, well, what could I, what can I actually say about the derivative of a of t? What could I symbolically write down aside from just sort of throwing my hands up in the air and saying, I don't know what that is? I mean, that's not very helpful. So implicit derivatives ask us to say, well, you might still be able to apply some rules and some thinking and some logic from the derivatives chart to the problem that you're faced with, even though you're not going to come up with a specific answer like cosine of t. You can still say something intelligent about what the derivative would at least involve. That's what an implicit derivative is it's trying to say, I know you're not going to be able to tell me the precise answer, but tell me something about it. Tell me at least, sort of like instead of moving 5 steps forward to get to the answer, which is what I sort of, let's say you needed 5 steps to get from the question to the answer. Well, implicit derivative is like taking like 2 steps of the 5 you would need, but it's the only 2 steps you can take. Now, 2 steps are better than no steps, right? So again, throwing up my hands in the air and saying, I don't know what the answer is, that's not helping at all. So an implicit derivative is I guess, designed, or the way you can think about it is, I can at least, let me do what I can do, and the things that I don't know, it's okay. I'm going to leave those as sort of unknowns. But I'll have sort of advanced the problem at least a few steps towards its solution. Okay? So now, the first couple are a little bit silly, but if I ask you, say, tell me about the derivative. I want to take the derivative, right? I want to take the derivative of. So our first example is an a of t, could be f of t or g of t or whatever letter you want, right? It's just a random function, any function at all. I say, all right, what could I say about the derivative of a of t? So I'm going to use our usual sort of notation here, right, to say, oh, I want to compute the derivative, or say what I can say at least about the derivative of a of t, some random arbitrary function. Well, here, again, I was able to do the derivative of sine, and I said it's cosine. Well, this is just a random function, so what would the derivative of just a random function be? Well, this is where this is kind of a smart-ass answer, I suppose, but, well, it'd be a prime of t, wouldn't it? Right? I mean, I know I'm really not saying much here, aside from that, just kind of the notation, really, more than anything else, right? That if I was looking at just a of t and I wanted to compute the derivative of that, there's not much I really can say, but the derivative of a of t, well, it's a prime of t, right? Just like the derivative of f of x was f prime of x, right? So, okay, I've really, that's really not terribly much more helpful. But that's also all I can say, right? I mean, I don't know what else I would even write down there. Okay, so that's a little bit of a silly example, but I'll be honest, don't forget it, right? In these problems, we're going to encounter situations where I'm going to want to take the derivative of just a function, an unknown function, b of t or k of t or whatever I'm working with. Well, all right, well, the derivative of that's just the derivative of that, right? I mean, there isn't much to say. All right, but in these other examples, we'll have something a little bit smarter to add. Okay, so how about the next one? So 2 times a of t. So if I'm coming along here and I want to say I want to compute the derivative of that, 2 times a of t. Well, again, I don't know. I'm not going to be able to say exactly what the answer is. But we have a rule in our chart that says if you have a coefficient, which is what 2 is, and you wanted to do the derivative, you would carry the coefficient over, and then you would compute the derivative of the rest. And you've used that rule a whole bunch of times. So believe it or not, that's actually, I've helped a little bit here, right? I know maybe it doesn't seem like I've done that much, but I've at least said something about this is all, that's all I could say though, right? That's all I can say about the derivative, is that if you have 2 times a function, well, the derivative of that, of this whole thing, would be 2 times the derivative of this piece. Okay, and that's it. That's all you'd have to do in this case. But maybe it doesn't seem yet why this is helpful, but it will when we get there. All right, now let's try one that's actually hard, or harder. So I want to compute the derivative of something like a of t, right? So a of t is just this unknown random function, but it's being squared. Okay. So now let me come back up here to our setup problem. So what if I have, let's say, sine of t squared? Now, again, we're going to be able to know, and hopefully you can all do this one pretty quickly, we're going to be able to write down exactly what the derivative of that is, because I know exactly who my mystery function is. It's sine of t. So you're going to be able to exactly compute that derivative, and if I give you 2 minutes, you'd be able to compute exactly what the derivative of sine of t squared is. But think about what steps you would do, or think about the rule or rules you would use, and I think, hopefully, within a few seconds, you're already thinking sine of t squared looks like a chain rule, doesn't it? And you would do the chain rule on it, and you would get your answer by doing the chain rule, wouldn't you? Well, a of t squared, which is what I'm looking at right now, I mean, is it crazy to say that that's still a chain rule? Because look at it. Doesn't it look exactly like a chain rule? It's one function plugged into another function, right? I mean, this is sort of our classic setup for the chain rule. And so let's humor me here, and let's just try to write out the steps of the chain rule and see what we come up with. So the chain rule here, chain, would say what? I'm supposed to find the outside function and the inside function. Right? Or in other words, I'm supposed to say this is one function plugged into another function. Okay, now if I was doing this one up here, the sine of t squared, I'm going to have faith in you all that you would have probably told me, I'm going to erase my little guy here, that this is the chain rule, and that I was taking sine, whoops, sorry, I ran out of space there, that says sine of t, and I'm plugging it into the t squared function, right? Hopefully you'd all have told me that. And you would have said, oh, okay, the derivative of that's 2t, and the derivative of sine is cosine. Okay, and you would have assembled your answer. Maybe I'll go ahead and assemble it, just since I'm already almost done with it. I would assemble my answer to the chain rule, which would be f prime with g plugged in, times g prime, right? So that would be 2 times g times times g prime, which is cosine. And that would have been my answer, right? 2 sine of t times cosine of t would have been my answer, which I have faith you would have all gotten correct had it been on the last exam. So what's the only difference between this guy and the one that I'm trying to do right now, this guy, is that I don't know what a of t is, right? Maybe it's sine of t, and if it was, that would be the answer. But let's mimic this, right? If I say, all right, this is still a chain rule down here, a of t squared is still a chain rule, because why? Because it's still one function plugged into another one. So what's the function I'm plugging it into? T squared. And what am I plugging into t squared? As funny as this looks, a of t, right? So let's do our usual check for the chain rule. Did I get the chain rule set up right? Is it the case that I have g plugged in for t, and that's what I have? Yes, it is, right? I have a of t plugged in for t, which is squared, which would be a of t squared. So I've got the correct setup for the chain rule, and in many ways this is actually even easier than the one I did up there in the corner with sine, I can still say the derivative of t squared is still, that's 2t. I can still say that. And now again, I don't have a lot of intelligent things to say about this, but what's the derivative of g? Well, if g and a are the same thing, which is what I'm saying here, well then I don't know, the derivative of g would be the derivative of a. Okay, that's all I'll say about that. But now let me assemble the chain rule, just like I did up here, right? I assembled the chain rule and I got an answer. Let me do the same thing. So if I assemble the chain rule here, what am I going to do? I'm going to say it's f prime with g plugged in times g prime. Okay. Now I don't want f's and g's in my problem, right? My problem started with a of t. So I want to, I want to leave a of t in my answer. So it's f prime, that's 2t, but with g, which is a, plugged in, times g prime, which is a prime. So I think if you do the chain rule, I'd end up with 2, and then g should be plugged in, but g is really a, times g prime, which is just a prime. Okay? All right. Okay, so I'll let that sit for a second. Think about that. Okay, so now, do I have is this a sort of final answer, so to speak? There's this, does this tell me everything I wanted to know? Well, probably not, but it's better than what I started with. When I started, I just said, tell me the derivative, or tell me what you could say about the derivative of an unknown function a that's being squared. Well, I didn't just say nothing. I gave you something here, right? Or we figured out something. We said, all right, well, whatever a happens to be, whatever a of t happens to be, the derivative of that function squared would be this. And what is this? This is, well, 2. Then whatever that unknown function was, plop it in right there. And then what should that be? Well, the derivative, right? The derivative of the unknown function. And in fact, if you do a little bit of a comparison here, let me erase my blue here, compare this answer with this answer. Now in this case, hopefully it's obvious, right? Playing the role of a of t in this example would have been sine of t, right? That's exactly what's playing the role of a of t. And what did my answer turn out to be? Isn't it true that this simply appeared right there, and the derivative of this is what appeared here? So isn't that exactly what I'm saying down here? I'm saying the derivative of this thing is 2 times whatever a happens to be times the derivative of that same a. So so I don't, squint again, sort of squint at those two for a second here. And just think about, okay, so it is the same. Hopefully you can see how it's a very similar problem. The only difference is that in this example with the a of t, the implicit derivative that I'm doing here, I don't know what a of t is. So my answer over here, that's the best I could say. But it is helpful, and it will be very helpful when we go to do these related rates problems. But moreover, it agrees with the one example we did over here, where I was actually saying, okay, if I give you what the specific function is, look, it appears there, and the derivative of it appears here. Well, that's exactly what I said over here. All right? So it is helpful, right, to be able to doing these implicit derivatives. Like I said, it moves you maybe halfway towards what would then maybe be a complete answer. And but that's as much as we could do, right? Because I don't know the true identity of a of t. So this is the best I could say about the derivative of a of t. Okay? So I'll go on to the next slide in just a second, right, and do a couple more of these. But think about this. Think about this setup here and this chain rule, because you're going to have to do this in pretty much every related rates problem. Now, the good news is that it's pretty much just always the chain rule, or easier, right? So it's not hard, I guess, but you have to do it, I guess, is maybe is what I'll say. So this will come up, and you'll be like, oh, that's why he was talking so much about this. So try to sort of tuck this away, at least understand, hopefully, the setup here, doing the chain rule each time, and being able to do this. If you're still a little foggy on why you would want to or when you will do this, that's all right. That'll come up in context. Okay, so how about just a couple other quick ones before we move on to real problems. So, come on. So how about, what about trig? Could I do the cosine of some unknown function a of t? All right, well, again, maybe I'll just jot up here in the corner. If I had cosine of t squared, you would hopefully have told me that that's a chain rule, because it's one function plugged into another function, right? Well, this is the same thing over here. I've got cosine of a of t. Now, the only difference is that a of t is unknown to me. But that's all right. I'm going to proceed just like the chain rule would say and see what I get. All right? So let me do the chain rule, or get the chain rule set up. So I'm looking for the outside function and the inside function. And hopefully, just like with this one up here, it's pretty obvious that its cosine is the outside function. And what am I plugging into cosine? Well, a of t, whatever that happens to be. Okay, now the chain rule, or the derivative of cosine is negative sine from the chart. And again, this is a little silly, but the derivative of g, well, if g and a are the same, then the derivative of g is the derivative of a. All right? So I'm going to put the pieces of the chain rule together and say, all right, what is the derivative then? So the chain rule says I should do f prime, but with g plugged in, times g prime. Okay, so f prime is negative sine, but I'm going to plug g in. But remember, g and a are the same, so it's really actually just equivalent for me to say, let's put a in there, and then times g prime, but g prime is a prime. So that's my answer. Okay? And again, if I did this one, maybe I won't do it out for you, but go off to the side if you want. Do that real one, right? That's a non-implicit or explicit problem where you can actually write down exactly what the answer to that is. But I promise if you do this one, you're going to get negative sine of t squared, for right here, times 2t. And what's the only difference? Well, the difference here is that you knew that this was t squared, so you could put that right there. And if that's t squared, if a of t is t squared, then the derivative of a is 2t. Okay? So the only difference is that since I don't know what a of t is, which I don't, I have no idea what that is, this is the best I can say, is, well, that's at least something. I've at least moved you a couple steps towards the answer to what is this derivative. Okay? All right, and I guess maybe just one more here since we've got it in front of us. 2 divided by a of t. All right, so, probably a couple ways to think about this problem. I think just from the last test and looking through the work you guys did, you sort of jumped all over the quotient rule whenever you saw a fraction, and that's okay. So that's fine, let's do that. Let's use the quotient rule, because it's a fraction, right? You don't really need it for this, but that's all right. Let's do it anyway. So the quotient rule says there's a top and there's a bottom. 2 is on top. And again, just sort of silly, in a silly sort of way, well, what's on the bottom? A of t, because that's what's on the bottom. Okay, I proceed with the quotient rule, which says I need the derivative of each of these characters. Now, the derivative of 2 is 0, right, because the derivative of a number just by itself is 0. And again, just in sort of a silly way, the derivative of the derivative of g prime, that's just a prime, because g and a are the same thing. All right, so I fill in the quotient rule, which says this should be, the bottom, g, which is a, times the derivative of the top, which is 0, minus the top, that's 2, times the derivative of the bottom, which is a prime, all over the bottom squared, which is, again, a. Okay, now that's 0, right? 0 times anything is 0. So really all I'm left with here is negative 2 a prime over a squared. Okay? And that's it. That's the right answer to what is the derivative. Now again, right, it's not complete in many ways, but that's as much as we can do right now. And that's actually going to be extremely helpful in moving us towards our answer in these related rates problems. So, all right, so I'll wrap this up now, and we'll go on to, I'll start the related rates problems in another video. But what's the deal here, right, with these so-called implicit derivatives is basically just we're looking at them, we're still using the rules from our chart, right? The chain rule, the product rule, the quotient rule, any of the rules. It's just that basically you're always ending up with like kind of a dummy in there, like G or F, depending on which one role it's playing, is pretty much always going to be sort of probably like a just dummy A of t or B of t or F of t or whatever function you're using. And that's all right, because it's still going to appear in your answer everywhere. Look, I mean, everywhere in my answers, A and the derivative of A appeared. And that's going to be, not only is that okay, that's actually good. Because what we're going to see when we now go over to these modeling, these related rates problems, is that we're going to have expressions for quantities and how they are related to each other. And we're going to be asking questions or want to know or have information about the derivatives or the rates at which those quantities are changing. So we're going to be very happy to see derivative, or A prime and B prime and C prime and whatever letters we're using, the derivatives of quantities we're going to be happy to see those guys pop up. Because that's basically what happens here, right? You're basically seeing kind of like, okay, I kind of am using the chart, but I'm kind of leaving bits sort of from the chart in my answers, you know what I mean? You're not just getting just all t's at the end. You're leaving these unknown functions in there. That's actually going to turn out to be a very good thing for us. So, all right, but the purpose of these problems was just to hopefully get you familiar with and hopefully get you competent in doing these implicit derivatives, because when they pop up, they will pop up in every single problem we do. If you mess it up, again, just like all word problems, this unfortunately is going to send you down a very incorrect path. And, you know, so we'll do lots of examples of these because, like I said, they'll pop up in every problem. But, okay, so the next video, we'll start the actual related rates, which is right here on this next slide, and also on the handout. So, okay.